Okay, hello, this is SD2K Productions and my OJ, and now we're going to look at how to find the eigenspaces and eigenvalues of a matrix that isn't like complete poverty. So this is a pretty cancer matrix, as you can see. Um, because the one in the video is two times the identity, and two times like this thing, which is that matrix. It's pretty kind of it's like really obvious that the eigenvalues are just 2 times 1. Like they're just two eigenvalues of 2 times 1. And then the eigenspace is also pretty obvious because it's literally this thing minus the eigenvalues in the diagonals, which is equivalent to finding 0. So yeah, pretty stupid. Meaning like the span of the two dimensions is the eigenspace, which is really dumb. So now to demonstrate a non-smooth brain example of this, we'll first try to find the eigenvalues, which yeah, the formulas and all are fine. Just the example is like horribly harebrained. So okay, so I did a few steps on the side now. And this characteristic polynomial, basically, you subtract this random, you call it lambda, that's your eigenvalue, and given original matrix, right? Um, the how to find the eigenvalues is where the determinant of the original matrix minus the lambdas on the diagonal is equal to 0. So I'll explain what that is right now. The determinant, and it's basically like turning this thing into a equation. So this top left times this, the product of this minus the product of this, all right, subtracted by, well, there are a lot of ways you can do it. Oh wait, I said that wrong. I'll say it the way I did it now. So I did it the bottom right times the product of this minus product of this. That's the first step. After that, you subtract this thing times the product of this minus the product of this, and then finally you add this thing times the product of this minus the product of this, and it's highly cancer. I haven't even solved it yet. I just like computed what the equation is. So it's the first part, second part, third part, 0. This is what they call the polynomial equation. So we'll solve that real fast. Okay, so I haven't solved it because it's such a donkey problem that like no human's going to want to do this because computers exist. In fact, allow me to show you the exact solution right here. Um, so load suka. All right, yeah. The real is 7.5437. Is approximate, right? And the complex is whatever. Now you look at the exact form. Yeah, I'm not solving that. This is why computers exist. All right, and let me show the exact form of the complex one. Yeah, look, pretty donkey. But yeah, going back to this, I'll tell you like how to find the eigenvectors, because like I'm not finding those, all right, but how you do those is basically for like assume that eigenvalue is 1. It's not, but just like given some eigenvalue like this thing, or I'll just try to plug in this 7.5 roughly, then you'll have the eigenvector, we'll call it v1, all right. uh that's equal to like this thing, null space of the characteristic or of the like matrix minus the eigenvalue on the diagonal. So it's simply 3 minus the whatever 7.5, 7, 1, 2, 5 minus 7.5 minus 2. Yeah, I'm doing it over here. And then minus 3, 4, 1 minus 7.5. Alright, so like I calculated the eigenvalues fine. The eigenvector, well, like everyone does it by computer now, so that's why you generally have an easy example, but that one is like insulting. I just made one up. That's why this one is pretty painful to do as well. This one's like arguably too hard. That one is too easy. I don't care. But basically, whatever vector you find that does that where this thing works, like this is really easy. It's literally there are like 10 ways to do this. Just like multiply the left side by the inverse, right side by the inverse. So what'll happen then? So I multiply like a inverse times this thing. All right. Oh wait, now give me a second. Oh, I messed up the last step. All right, but so now I just need to go about how to find the null space, right? So then basically turn this thing, they call this A, all right? Then what you can do is LU factorization, and then all you have to do is just solve the U part, because that like as long as you have all ones on the L, just solving U times this thing is equal to 0 is like really easy. It's the equivalent of doing like x is equal to 1, x plus y is equal to 2, x plus y plus z is equal to 3. I'm just saying that it'll like cascade pretty easily in the solutions, and then that's how you'll find your eigenvector. So we have computers to do this now, so yeah, whatever. And that's about it.